Well, students, we are studying error analysis in polynomial interpolations. In the last lecture, we have derived the formula for mathematical error and also learned how to find estimates for the mathematical error. In this lecture, we will study the arithmetic error involved in polynomial interpolations. Let Pn of x be the interpolating polynomial of a function f at the nodes x0, x1 up to xn, and let Pn tilde be the interpolating polynomial for the function f at the same nodes, but now the function values are not taken accurately, but only taken with a floating point approximation. We will consider the polynomial interpolation in the Lagrange form, and we are interested in studying the arithmetic error, which is given by Pn of x minus Pn tilde of x. Let us use the notation epsilon I for the error involved in the floating point approximation of f of xi when compared to the exact value of f of xi. Further, we will use the notation epsilon with infinite norm as the maximum over all these epsilon i's, where I ranges from 0 to n. Remember, this is just a notation. Then the arithmetic error, which is given by Pn of x minus Pn tilde of x, can be written in the Lagrange form as I is equal to 0 to n. For Pn of x, we have f of xi into Li of x. If you recall, Li's are the Lagrange polynomials, right? Minus for Pn tilde, we have taken the function values as the floating point approximation of f of xi's, right? Therefore, that will sit as the coefficient, and then the Lagrange polynomials Li of x. That can be written as sigma I equal to 0 to n f of xi minus fl of f of xi into Li of x. Now you take modulus on both sides and take this modulus inside the summation and use the triangle inequality to get this as less than or equal to sigma I equal to 0 to n mod f of xi minus fl of f of xi times mod Li of x, right? Now, these are nothing but epsilon i's by notation, and further, we will take maximum of all these epsilon i's, and for that, we have assigned a notation norm epsilon. Therefore, we will dominate all these terms in the summation by norm epsilon infinity, and thereby we will have this less than or equal to norm epsilon infinity times sigma I is equal to 0 to n mod Li of x. I'm trying to find an upper bound for the arithmetic error. That's what I'm trying to do. Assume that you know all these values, and therefore you also know this norm epsilon, but still this cannot be considered as an upper bound because it still involves the variable x. So we somehow have to freeze this variable x. For that, we will again dominate each of this term in the summation by its infinite norm over the interval in which we are interested in, say I, right? Since Li of x is a function, which is a continuous function, therefore you can always find the infinite norm of that function over the interval in which we are interested in, and then dominate your function mod Li of x by this infinite norm. That will finally give us the estimate as norm epsilon into sigma I equal to 0 to n infinite norm of Li, right? Now, this inequality, that is mod A E n of x, is less than or equal to norm epsilon into sigma I equal to 0 to n. Norm Li holds for all x in I, right? Therefore, this inequality also holds for that x for which this term attains its maximum norm, right? Therefore, you can write norm AEN is less than or equal to norm epsilon into sigma I equal to 0 to n norm Li, and that gives us an estimate for the arithmetic error involved in the polynomial interpolation for the function f at the nodes x0, x1 up to xn. So far, we have obtained the upper bound for the arithmetic error, which is given by this. Now, let us have a close look at this upper bound. We can see that the upper bound might grow significantly as we increase n, especially when the node points are equally spaced. What is meant by node points are equally spaced? Suppose you have node points x0, x1, x2, and so on up to xn. Let us consider up to x5. The distance between the consecutive nodes are equal. That is what we meant by saying that the nodes are equally spaced. That is, the distance between these two nodes, say h, is same as the distance between these two nodes, and so on. So in this case, you can write any node xi plus 1 is equal to xi plus h, right? Say for instance, x3 is nothing but x2 plus h, right? So that is what we are writing here, and we generally take x0 to be a, which is the lower bound of our interval, and xn is generally taken to be b. And since xi plus 1 is equal to xi plus h, you can always write it as xi minus 1 plus 2h, and so on. You can go ahead, and finally we will reach x0, and we will have plus ih, right? Since we take x0 as a, we can write xi plus 1 as a plus ih. That is what we are writing here. Remember, this I is not the complex number, but it is just the index running from 0 to n. We never work with complex numbers, therefore we should never get confused with this I. Whenever we have a general x in the interval a b, which is not equal to any of the nodes, that can be always written as x is equal to a plus this distance can always be written as a multiple of h, right? Let this distance be, say, d, then you can always write d is equal to eta h, where eta is obviously equal to d by h, right? So you can always choose a real number, eta, such that x is equal to a plus eta h. Now with these notations, that is xi equal to a plus ih and x is equal to a plus eta h, we can write the Lagrange polynomial like this. If you recall, the Lagrange polynomial Lk of x is given by this expression. Now I'm putting x is equal to a plus eta h and xi as a plus ih. Therefore, x minus xi can be written as eta h minus ih. Similarly, in the denominator also, you will have a h gets cancelled, and we will have this expression for the Lagrange polynomial when the nodes are equal, right? We should note this. When the nodes are equal, we can write the Lagrange polynomial Lk of x like this. In this, you can always write the denominator term as k factorial into n minus k factorial. This is a well-known elementary formula. And similarly, the numerator can be dominated by n factorial. Once if you use these two facts in the definition of the Lagrange polynomial Lk of x, we can see that mod Lk of x is less than or equal to, why less than or equal to? Because numerator is only dominated by n factorial. Therefore, your Lagrange polynomial Lk of x is less than or equal to n factorial divided by, use this one to write k factorial into n minus k factorial. And again, the same usual argument that this is true for all x in I, and therefore it holds for that x for which the infinite norm of this function is achieved. Therefore, we can write norm Lk, sorry, this is less than or equal to n factorial divided by k factorial into n minus k factorial. Now take the summation over I is equal to 0 to n. You can see that the right hand side of the inequality is nothing but 2 to the power of n, right? 1 plus 1 to the power of n will come. Therefore, we see that summation I is equal to 0 to n, infinite norm of the Lagrange polynomials Li is less than or equal to 2 to the power of n. From here, you can see that the upper bound is increasing quite rapidly as n increases. Well, that doesn't mean that the left hand side should also increase. It may still stay very close to 0 while the upper bound is increasing to infinity. But what this inequality says that since the upper bound is increasing quite rapidly, it gives a possibility that left hand side may also increase quite rapidly, but it doesn't give guarantee that the left hand side will even increase, right? So to confirm that, we will do a numerical experiment and see how this term is behaving with respect to n. So for that, what I'm doing is I'm considering this term. Remember, if I take infinite norm in each of this term, that is what is sitting here as the left hand side. So here, just to have a feeling of how this function behaves, let us give a notation for this as L of x, and let us see the graph of this function for some n. Let us start with n equal to 2. The graph of the function L is given like this. You just keep watching the maximum that is attained by this function L of x, right? The maximum for n equal to 2 is nearby 1.25, right? Let us go to increase the value of n and see how the graph of the function L of x looks like. When n is equal to 8, for instance, the graph of the function L of x looks like this. Again, you can notice that the maximum of this function L of x is now very near to 11. Previously, it was just 1.25. Now it grew to 11. And then I went further to n is equal to 18 and see that the maximum of the function L of x had grown quite significantly, and it is very near to, in fact, 3000. So from 8 to 18, it has increased quite rapidly. That shows that not only the upper bound is increasing quite rapidly, the left-hand side also takes the opportunity of the room given by the right-hand side, and it also increases quite rapidly. That is what we have understood from this numerical experiment. In fact, we will plot the graph of the left-hand side more precisely as a function of n. So in this graph, the x-axis is taken as n, and y-axis is taken as the left-hand side term. Remember, we have shown that this is less than or equal to 2 to the power of n, right? So this graph shows that the left-hand side is in fact growing exponentially as well. This is a dangerous warning for us because if you recall, unfortunately, this term, that is Mn in our notation, is sitting in the upper bound of the arithmetic error, right? And we have seen that this is less than or equal to norm epsilon times 2 to the power of n. That shows that even if this term is very small, as long as this is not equal to 0, however small it is, as you go on increasing n, this number at one stage of n will become significantly large. Again, that gives us a room for the arithmetic error to increase. Remember, this doesn't mean that the arithmetic error will indeed increase, but it gives a possibility that the arithmetic error can increase drastically. Again, we will see an interesting numerical experiment where this arithmetic error indeed increases and spoils the entire approximation. Before taking up this interesting example, let us complete the theoretical discussion. We still need to find an upper bound for the total error. If you recall, total error by definition is the sum of the mathematical error and the arithmetic error, right? Now let us take the infinite norm on both sides and see that the infinite norm of the total error is less than or equal to the infinite norm of the mathematical error plus the infinite norm of the arithmetic error. We know the bound for this term and also we know the bound for this term. We can simply apply these bounds. Let me just put the bound for arithmetic error because I'm presently interested in showing you how disastrous the arithmetic error can be in amplifying the total error. So I'm just putting the upper bound only for the arithmetic error. Similarly, you can also put the upper bound here. And you can observe, as far as the arithmetic error is concerned, Mn increases exponentially with respect to n. This is what we have learned just now. Therefore, the presence of floating point approximation, that is, as long as this term is not equal to 0, regardless of how small it is, you can see that since this term increases exponentially, for a large enough n, this term may be very large. Therefore, even if your mathematical error is very small, you may land up with a significant total error for large enough n. This is because of the presence of the floating point approximation. So one has to be very careful in working with the polynomial interpolations, especially with equally spaced nodes. Although mathematically we understand that as we keep on increasing n, we get better and better approximation. It doesn't mean that we can go on increasing n. Let us see the danger of go on increasing n with the hope that we get better and better approximation for our function. Let us take up the example of f of x equal to sine x in the interval 0 to 1. Recall that we have considered this example while learning the mathematical error. And if you recall, we have also derived the upper bound for the mathematical error in this case as 1 by n plus 1 factorial. So in this example, you can see that as n tends to infinity, your mathematical error will go to 0 quite fast. That gives you the guarantee that the mathematical error is also going to 0 as n tends to infinity. It means that as far as the function f of x equal to sine x is concerned in this interval, even if you work with equally spaced nodes, mathematically your polynomial interpolation works very well. Let us see when we go to implement this idea on a computer what happens. Because when you go to implement it on a computer, your computer will introduce the floating point approximation and thereby it will give you a non-zero value for this term, right? Let us see in this case what happens when we keep on increasing n. Let us start our experiment with n is equal to 1. Now I'm representing the graph of sin x by star and the graph of the polynomial interpolation by the solid blue line in order to have a better visual effect. In this case, the total error is approximately 0.06 and the mathematical error is something less than or equal to 0.5, right? And this mn in this case is 2. Let us now keep on increasing n and see how the graph of the polynomial looks like to get an idea of how well it approximates the sine function in the interval 0, 1. And we will also have an observation on these parameters to see how these errors are increasing. Let's go to n is equal to 2. You can see from n equal to 1 to n equal to 2, the quadratic polynomial is of course approximating the sine function quite well, and the total error also improved very nicely. As expected, mathematical error is decreasing. Now let us jump to n is equal to 10. You can see that the graph of the interpolating polynomial P10 is almost coinciding with this graph of the sine function. The total error is significantly small and the mathematical error is also very small. Now let me jump to n is equal to 25. Well, graphically, we don't see anything going wrong. It is still giving a good approximation. But look at the total error. When n equal to 10, we had something into 10 to the power of minus 30, right? Now, we increased n equal to 25 and the total error became 10 to the power of minus 10. That seems to be a bit bigger than the previous ones, but you look at the mathematical error from 10 to the power of minus 7, it has decreased to 10 to the power of minus 25. That is quite expected because it is bounded by this nice number, whereas the total error seems to be giving us a warning now, right? Let us not listen to its warning. Let us go on and increase n now to 50. Well, graphically, we don't see anything going wrong still, but you can see that the total error is quite big when compared to the total error with n is equal to 25, right? You see, now it is 10 to the power of minus 4. Well, mathematical error is very good. That shows that mathematically we are still doing very well. That is quite natural because we already know it from this. The total error is now giving a more severe warning for us. Let us not listen to it. Let us go ahead and take n is equal to 65. It means I'm trying to approximate sine function by the polynomial P65. That is what is here. And it is represented as usual by the blue line. You can see that the error is quite visible now at the end points, right? And you see the total error is now significantly large, while the mathematical error is still very nicely decreasing, and it is at a magnitude of 10 to the power of minus 90. It means mathematically you are almost converging. However, your computer is showing up something very bad. That shows that this error is purely because of the floating point approximation. Remember, I am computing this on a very powerful latest machine, 64-bit processor, and double precision I am computing. Let us go on and compute the interpolating polynomial with n is equal to 75. You can see now the total error is 570. That's no way near to what we would like to call as an approximation to f of x. Again, you see the error is mainly popping up at the endpoints of the interval, right? Look at the mathematical error. Well, this shows that mathematically we are doing very well, but computationally something disastrous is happening. Finally, let me show you the plot of P80. the total error is 7060. You can see that sine nearby almost say 0.95 is equal to 7000. That is what your computer is giving you the value. You can understand from here how dangerous it is to work with computers blindly. Well, a computer is a very powerful tool for computation, but one has to understand its limitations very clearly before using computers in scientific computing. Otherwise, we may land up in a disaster like this. Hence, doing a rigorous analysis of your methods before taking the method to a computer is very, very important.